Welcome back. Hope you had nice holidays and a nice break. And we're going to continue now with our introductory exploration of statistics. We're going to see with a higher frequency now for the 2 months to come, and we have a lot of material to cover, which is going to be fine. So we're going to get through all the material. We're going to have time to practice. We're going to have time to put this into practice also in R. And but it's a lot of material. So it's your first exploration of statistics. So some aspects will be a little bit more challenging now. So the midterm is on the 14th. We cover chapters 1 to 9, I believe. Confidence interval is chapter 9. So we will, from now on, we will talk today about normal curves, standard decision and set scores, then do hypothesis testing on Wednesday. And the next week, we're dedicating the 2 lessons for confidence intervals, effect size, and statistical power, which is a continuation of the hypothesis testing. And then we're going to do a lab day, which also allows us to look at use cases of hypothesis testing and confidence intervals. And then we're going to do a review session on the 9th, and then on the 14th, we have the midterm. So this is chosen by design because I wanted to split the class into that part that essentially does the descriptive statistics, starts a little bit with inferential statistics, but basically here after the midterm, it's going to get more involved. So it's going to be single sample t-tests. We're going to get into t-distribution. We're going to do analysis of variance where we have several groups, and then get into regression methods, and then conclude with chi-squared as the last test that we will discuss. Okay. Any questions to anything of the syllabus? Next week, we're going to have a discussion post again, and that's for you to review. Good. Let's quickly do an attendance. That we have this over with. I guess biological chemistry goes over today. I think that's why more are missing. Okay, Sheila Bakshi. Dina Bezalel. Hi. Kayla Kagan. No? Alexandria Cohen. Hi. Talia Dina. Fini El Kubi. Hi. Kira Urba. Hi. Abigail Goldberg. Sarah Grossman. Hi. Jaya Hill. Bruce Kaplowitz. Hi. Yardena Lipson. Emma Machia. Hi. Maya Melul. Hi. Tiferet Mondro. Hi. Hi. Yeah. Esther Nahon. Hi. Maxine Brafta. Hi. Inbar Rade. Hi. Evia Rosenkranz. She's coming for sure? Yeah. Okay. Rachel Schmuel. Hi. Alison Warren. Hi. And Hannah Wiesen. Oh. Okay. All right. So on the module, you have a couple of things to download. You have the PowerPoint presentation, which is essentially the lecture for today. We have a file called normalcurve.xlsx. We have normalcurve.r, which hopefully we will get to, but we'll see. Then we have a happiness report, raw data.xlsx, and we have a set score table, which we will see in a bit what that is all about. We will get started with the PowerPoint presentation. We'll quickly go back to discuss the norm distribution. Now, just as a quick recap, just about the material that we've discussed so far. I just quickly want to go over the syllabus. So you remember what we did. So we have mainly discussed so far descriptive statistics. So we are now slowly starting to come into inferential statistics. So we talked in module 2, we talked about an introduction to statistics, research and design, which basically gave you an idea about hypothesis testing, research design, design of various studies, comparative analysis between groups, random allocation and assignment. We also talked about the three mainstays, basically two that are mentioned by Nolan and Heinz, which is descriptive statistics and inferential statistics. With the third one being research and planning of research studies and analytic approaches to these data. Then we talked about frequency distribution. I hope you all remember the example of the volcanoes, where we utilized the number of volcanoes in a country to quantify the actual number of countries with a certain number of volcanoes contained, which was the frequency table, right? So we had a number of volcanoes for each country, and then we mapped out frequencies of volcanoes within the country from 1 to 17. And we quantified the number of countries in these respective entries, which allowed us to produce a frequency table. If you break this down into subgroups, and you do 1 to 5 volcanoes, for example, you get what is called a grouped frequency table. The grouped frequency table essentially gives you an overview in larger chunks. So all of this essentially is to depict data in a digestible format, and essentially a histogram, which we have discussed with the visual display of data in module 4, is nothing else but a graphical depiction of the occurrence of each individual numerical value as a function of the actual numerical value. This also can be depicted as a dot plot or as a box whisker plot, where the box whisker plot essentially shows you the middle 50% of your data, with showing you a box for Q1 to Q3, where Q1 is that numerical value below which you capture 25% of your population, and Q3 is that numerical value below which you have 25% of the higher part of the population, and in between you have that middle part contained within the box, with the median splitting all entries basically in a lower 50% and a higher 50%. Q1 and Q3 essentially also characterize the so-called IQR, the interquartile range. This was basically what we discussed in more detail in central tendency and variability, where we talked about the markers of central tendency, which was the mean, the arithmetic mean, which is the sum of all entries divided by the number of all entries, and then by calculating or estimating the median, which is basically that numerical value that splits the data in at lower 50% and higher 50%. The markers of variability we discussed was the standard deviation, where basically the standard deviation is calculated as the individual deviation of each point from the mean, squaring this deviation to get a squared deviation, summing all these squared deviations to the so-called sum of squares, which I flag as a very important marker because it will come back. It will reoccur with ANOVA and regression analysis. And then dividing this sum of squares by the number of entries, which gets you to the average squared deviation, which is the so-called variance. And the square root of the variance then essentially gets you to a standard deviation. So this is the most important marker of variability, essentially, that I highly encourage you to memorize. Then we have the IQR, aforementioned Q1 to Q3, also gives you, particularly for non-normally distributed data, an excellent marker of variability within your data set. Good. All of this essentially then builds the pathway into sampling and probability. I think that's quite important to memorize as well. So with sampling, you mean to always have a random sample of your population, although it's never possible, because it always will be very difficult to randomly sample an entire population, right? So therefore, you take subsets that you hopefully will find to be representative of your population, and they're quote unquote generalizable, with a high level of generalizability or high level of external validity, which is the technical term for it. Then we utilize this also to estimate the probability of estimating to randomly pick an individual with a certain condition from your sample. So essentially, when you think of a so-called prevalence of a disease in the population, and let's say you have in the population of New York City, you have a quote-unquote prevalence of diabetes of 10%. If you randomly pick one individual from your population, you have a probability of 10% that this individual will be diabetic. If you build subsets, let's say you have a sample of 10 that you randomly sample from your population, the prevalence in your subset should also be 10%. It's likely not, because it's a small subset. So your accuracy of your estimate will kind of suffer from a small sample size. So therefore, the larger your sample size, the more accurate the representation to your population will be, which is essentially also what we will be discussing today. It's also imperative and important to understand the basic principles of probability. So if you roll a die, essentially the probability of rolling a 6 is 1/6. If you roll it twice, it's two mutually exclusive events. They're independent from each other. That means you will have to arithmetically multiply them. So it's 1/6 multiplied by 1/6. And essentially these are independent events. And these principles are to be employed also when you randomly pick from a population, right? It's always 1/10 that would give you the probability of drawing a random diabetic from your population. So this is important to understand how samples may be differing from populations, because that's what we will be calculating and doing on Wednesday when we do hypothesis testing with the so-called STAT test. But let's not get too far ahead. Let's first look at normal curve standardization and STAT scores. Any questions so far on anything? I hope all of this is still somewhat fresh in your memory. But basically, as a quick recap. So all of the tests, except for the chi-square test, are so-called parametric tests. Parametric tests are tests that have an assumption about the distribution of the underlying data. And this main assumption is that it's a normal distribution. It's normally distributed data, which may not always be correct, but in principle, you get away with that assumption as soon as your sample size exceeds 30. That's kind of this magical threshold statisticians use. But basically, the normal curve is considered a bell-shaped symmetric curve that is unimodal, basically has only one peak, is symmetric, and it is defined mathematically. So it's the foundation of inferential statistics. And when I say defined mathematically, I included an Excel spreadsheet in which I was a little creative. I mean, not really creative, but a little trying to make this a little bit more tangible. So this normal distribution curve is essentially defined by a formula that is stated down here. So basically this formula is complicated. You don't need to learn it by heart. You don't need to know it. But basically I wanted to show that this essentially follows a pattern and a clear function that is characterized by sigma, pi, mu, and the variance here, combined with Euler's number. So you have here an individual X that allows you to transform and characterize each individual entry in this data set. So this is the definition of the normal distribution curve, which will in the following be important when we do standardization and the percentile estimation. So it's a defined mathematical function that essentially allows you to utilize the normal distribution in all future endeavors. So basically, it's important to keep in mind that the sample size is important not only for the estimation of a true population mean or population proportion, it's also important in relationship to the shape of this distribution curve. So the larger the sample size, the more likely this sample size will basically resemble a normal distribution curve. So when I say you get away with using parametric tests after 30, it doesn't necessarily mean it's really normally distributed, but you can assume it is to an extent that is acceptable. So as the size of the sample approaches the size of the population, the shape of the distribution tends to be quote unquote more normally distributed. So if you have your sample of 5, you can't really see that normal distribution represented by your data. If you look at the same histogram with a sample of 30, it shapes a bit more like a normal distribution. And if it then is being expanded to 157, which is that data set that I have attached with the happiness scores, you essentially see more of a normal distribution in that data. So as the sample size increases, the shape of the distribution becomes more like a normal curve. So what variables are normally distributed? So it's a very wide spectrum of variables that are potentially normally distributed. Essentially, biological parameters are most likely, to a large extent, to a large number, are normally distributed. Skewed data can also be found. Classically, so to move away from biological variables, classically skewed data distribution, for example, is household income, where you basically have the 1% very much to the right, whereas the bulk and the majority of households basically will be around the lower end. So basically you have a skewed distribution that is skewed to the right. In biological samples or in the medical world, you would, for example, have parameters that for a reason are skewed in one direction, to be rather skewed than normally distributed. Classical example from my world are inflammatory parameters, where somebody who is healthy doesn't have inflammatory parameters circulating in a high concentration. Once the individual gets inflamed, then inflammatory parameters can be extremely high. So essentially that gives it a skewness or the right skewness, classically situation. When you have something like blood pressure, this is more likely to be normally distributed because it basically gravitates and centers around quote unquote normal, healthy blood pressure. So now the question, can nominal categorical variables be normally distributed? That answer is basically no, not by the nature, because they don't contain a continuous variable. You could hypothetically, with a grouped frequency table, if you have an ordinal data set, then hypothetically you could think about a normal distribution amongst this, but it's not formally nominally considered a normal distribution. Also, when you have dichotomous variables like diabetes, yes, no, that also is basically a 0 or a 1. So you also don't have a normal distribution there. What could be normally distributed, though, is when you draw a large number of samples. So basically you draw 100 individuals out of the population of New York City, and you have one estimate of the prevalence of diabetes in that one sample, you get 1%. Then you draw a second sample, you get a second percentage. If you do that 50 times, you get 50 different estimates of the proportion in the population. This is normally distributed and will essentially be used for hypothesis testing with proportions. So that's called a normal approximation. So these proportion estimates from different samples, they are normally distributed, but that's different than what is meant with this question. So generally, nominal categorical variables are not normally distributed. So, but back to the normal distribution curve. Okay, so the normal distribution curve basically is a symmetric bell-shaped curve defined by a mathematical function that basically has at the peak, at the so-called mode, also the median, which splits that distribution curve in the lower 50% and the higher 50%. If it's really beautifully, and the optimal normal curve also has the mean at the peak. That means the median as well as the mean split the normal distribution curve in a lower and an upper 50%. So this being said, you can now use a method called standardization to characterize and standardize your normal distribution curve. What you essentially do is you can express every point from your data set as a standardized set score that basically is the distance of that point from the mean expressed as the number of standard deviations that are in between the mean and that score. What does that mean? You have here a normal distribution curve. You have the set right here. That set equals 0. That's the mean. If you have now a set of 1, this is 1 standard deviation above the mean. If you have a set of -1, that's a standard deviation, 1 standard deviation below the mean. And you can continue this. You can have like 1.5 or 1.6 or 2 or 3. So you basically can standardize the entire normal distribution curve using standard deviations and this formula. So X here is the individual score. The individual score X minus your mean mu. Also, please remember that when you have a mean for a sample, you have an M or an X bar with a bar on top. If you have a mean in a population, you have a so-called mu. That's the Greek letter mu. If you have a standard deviation in a sample, you have an S or an SD. If you have a standard deviation in a population, you have a sigma. So this is important to keep in mind. Also, at this point, we're dealing with population as a concept. We're not yet on the sample level. We will get to that in the second half of the semester. So the set score is now calculated as X minus the mu. So that's the difference between the numerical value you're interested in and the numerical value of your mu. So this difference, you're standardizing now in how many standard deviations are fitting in between that two values. And if you have here an example of a set equals 0 of 70, so that's your mean. So 70 is right here. If you have a set of 1, you have 80. If you have a set of -1, you have 60. The set of -2 is 50. And the set of 2 is 90. The set of 1.5 is 85. Simple, right? Yes. So let's practice this in Excel. So keep this in mind. So keep this relationship in mind. So this is the situation, right? And so this is the example. If we're going a little up and we take this formula, we take this formula now. So each individual set is calculated as an X, which would, for example, be here 80, minus the mu, where the mu is 70, divided by the sigma. So now we know that the standard deviation is 10, right? From 70 to 80, that's 10. So our sigma is 10. Our mu is 70, right? You've seen that. And if we want to calculate now our set for value, let's say 80, is now the individual x80 minus the mu divided by the sigma, right? So that's 1. So it's 10 divided by 10. So that's 80 minus 70 divided by 10. So if we're locking this in now and we say, okay, our G10 we're doing now this formula here. So this will now be H14, which is our x, minus the mean divided by the standard deviation sigma. This gets us to a set. So now if we're interested in, let's say, 95, we would look at a set score of 2.5, right? So it's the same formula. The same formula will also derive this set score. So it's basically individual x of 95 minus the mu divided by the sigma. If you are only interested in, let's say, 74, this is a set score of 0.4. So it's just you standardizing according to standard deviation. So you just calculate the difference and you divide it by the sigma. Gives you the distance from the actual value. If you take something less than the mean, arithmetically, again, we're going to go downwards. So it's going to be a negative set score. So now it's minus 0.7. So you're basically standardizing into negative sets and positive sets. Okay. So this being said, why is this important? Because what you want to do, you want to understand your normal distribution and the relation of each individual point in that normal distribution, because essentially, and cute depiction, so you basically you have a small dog and you have a large dog. The mean would be something in between, like a terrier-sized dog. So the small one is basically a negative set score and the big one is a positive set score. So you're basically quantifying according to the numerical value of that point of interest. However, you can, and this is now interesting, you can also calculate this backwards. So if you take the formula from before, you have x minus mu divided by sigma equals set. You multiply set by sigma and you add mu to set multiplied by sigma. You basically rearranged to have now the x expressed on the left-hand side. Therefore, you can calculate each individual point of interest just according to its set score. So this is the other way around. So going to that formula and the Excel spreadsheet, essentially, if you are calculating now, let's say you want to have 0.35 set score, 0.35 set score, you basically calculate this set multiplied by your sigma plus your mu will basically give you now your set, your x. So this is basically reversing that formula. Basically, it's simple rearrangement, and now just looking at it from the different value, from the different angle. Okay, so that's basically the other way around, just going backwards. Simple, right? So a set distribution then, so basically you're now transcoding your histogram and your normal density curve and your normal distribution from numerical values into standardized scores. So you have now a set distribution. which is normal distribution, just standardized as set scores. The standard normal distribution and normal distribution of set scores. So why are you even, yes? Excuse me? The set distribution and the normal distribution? So it's just a regular normal distribution. If you have numerical values and you have blood pressures, and you want to just standardize each individual value, you just have the same normal distribution, but now it's not numerical values anymore. It's not blood pressures anymore. It's basically set scores standardized to those blood pressure distribution where you have a mean and the standard deviation, and each individual point was now transcoded into a set score. So it has the exact same shape. It's just not individual blood pressures anymore. It's basically just set scores.
Why would I rather see that?
Thank you for that question, because because you want to compare apples with oranges, and you want to compare parameters that variables that you essentially could not compare to each other. And the apples and the oranges, yes, it's a cute example and it's a cute way of depicting this, but essentially a better example is this. When you say you have here a psychometric research of emotions, you have all emotions, fear and disgust, and you want to compare this for individuals for some shape or form, and you want to compare this prevalence in terms of their magnitude, you would need to standardize them to make them comparable based on that distribution within your sample population. And standardization is one way how to do that, because you take population parameters, you take the sigma, you take the mu, to basically characterize each individual point. And thereby you can basically make them comparable amongst each other. But this is basically not where this stops, so it goes further. So set scores tell you where the value fits into the normal distribution. So based on the normal distribution, you will basically have also the possibility to express so-called percentiles. So we talked about the median, right? So the median splits the entire distribution into two parts, a lower part and an upper part. We also talked about the IQR, the interquartile range. The interquartile range is essentially the middle 50%. So this is Q1 is below which 25% of all your data points are. Q3 is where 25% of your upper part data is. So 25% of your data set will be above a Q3. So these are percentiles. So Q1 is essentially the 25th percentile. Q3 is the 75th percentile. So it basically, if you have an entire data set and an entire distribution, you can basically quantify them as 100%. This is 100% of your data. So now you have 1%, 1% is less, 2%, 2% of all the data is less, 3, 4, 5, and you go on until like 25, 50, 75. Set scores will essentially allow you to characterize them, because we've seen the mathematical function of the normal distribution incorporates each individual point, the sigma and the mean. So the function, the normal distribution per se, is basically characterized as a function of the individual points or each individual set score, because the standard deviation at the mean is basically also leading to the calculation of the set score. So this being said, you can actually use this to characterize your entire normal distribution curve as percentiles or percentages. Basically, the assumption is that you have from the mean to set of -1, you contain 34% of your data. From a mean set score of 0 to a set score of +1, you again have 34% of all your data. So basically from -1 to +1, you contain 68% of your data. From -2 to +2, you capture 95.7% of all your data, which is here 34 plus 14, that's 48, plus 34, that's 82, plus 14 is 96. Rounding it up, but yeah, it's basically 95.7. The rest of the 2% that are out here in the tails, this is basically where you get from 2% to from 2 standard deviation to 3 standard deviation. That basically rounds it up. So within +3 to -3, you capture 99% of all your data. And then the outliers are just distributed all the way out. Hypothetically, that function that I've shown you that characterizes and defines the normal distribution curve, that actually is an asymptotic function. So it basically continues ad infinitum. Why is this now relevant? Because you can essentially express each individual entry here on your normal distribution curve with a set score. And you can say what fraction of your population is below a specific set score. And this is basically, so for, okay, let's backpedal a bit. So this 68, 95.7, 99% rule is called the so-called empirical rule, rule of thumb, or the rule of Chebyshev, a mathematician who first described it. And you will find different terminology for it, but essentially that's what it basically characterizes. It's the characterization and standardization of the normal curve. So why is this important? You also have in the module a set score table, which is quite a busy table, and I have a feeling you're not going to like it much. But it is very central, and it's very central to understand how to read it. So you're basically looking at rows and columns. The rows are basically giving you set scores up until the first decimal. So if you go all the way down to 0, a set score of 0 is basically splitting the population in half. So everything that is negative are the lower 50%. So 0 is basically 50%, -1 is here 0.1587. So then lie, it's 16%. Right? So essentially, the further you go down here at -2, you have 2.3%. So basically, the set score table characterizes the entire normal distribution curve according to percentiles. And that's actually quite important to understand, because not only does it allow you to understand what's less, it also allows you to understand what's higher than that value. Because if you say, okay, so I have a happiness score of 70 and a sigma of 10, and now I have -1 as my numerically happiness score of 60, I know that 16% are smaller than my happiness score of 60. But I also know, assuming that the entire distribution curve basically sums up to 1, because it's 100%. 100 minus 15.87 means that 84.13% of my population is going to be having a higher happiness score as compared to my happiness score of 60, which is set score of -1, right? So you can basically utilize this in both directions and quantify it in both directions. Good. Okay, so this is the set score table. In the same fashion, you're reading positive set score. Yes, please.
You would never have numbers larger than these in terms of like will never be less than -3.4.
Yes, you do, because it's an asymptotic function. So you basically, if you go higher, your percentage will increase or decrease as well. Or if you go lower, it will decrease. If it goes higher, it will increase, but it will never reach 0. It's just the increments are getting smaller and smaller and smaller. It's a non-linear function. Makes sense? Well, quite excessively actually for the rest of the semester. So you use the concept quite often. So where you, for example, use it quite frequently. I don't know who of you wants to go into medicine. Yeah. So if you want to go into medicine, for example, these percentiles are super important when it comes to child development. You will have in child development, you will quantify the growth trajectory of an individual child according to percentiles. And that percentiles is basically reference to population of children at the very same age. So you have this percentile trajectories for each age of the child. So it is quite important because it characterizes an entire population. So let's say you have a child where you actually you have a suspicion it doesn't digest well, it doesn't eat well, or it's for some other reasons, it's some abnormalities, it doesn't thrive, it doesn't grow. So you're basically comparing that individual child, your X, to your overall population of children at that very point, and you know how well the child grows. Make sense? I know I'm trying to bring it in a concept that kind of is easier to grasp, but it's a super important parameter. It's really important to understand.
So can we like follow through with that example of the kids so that if they have like a C-score?
Yeah.
If
Okay, let's assume you have a population study where you have characterized 2,000 kids. So that's usually that's population health data that was quantified. Sometimes those reference values, some of them have been developed in the 70s and 80s. So they basically took 2,000 babies, 2,000 kids at the age of 3 years, and they know the kid has to have, I don't know how much does a kid weigh when it's 3. I'm not sure about. But like, so you have a certain reference values and you have a mean from that population, and you know that below that mean you have 50%. Above that mean you have plus 50%, you have the upper 50%. And if that kid that's in front of you now in your practice is basically having a standardized set score of less than what constitutes the mean, which is a set of 0, you know that kid fails to thrive and needs to be investigated for whatever conditions you suspect.
And then why do I use like the inner part of the chart?
Which part?
So then where do I then look at the chart?
Okay, so if so these are positive, for example. So if that would be more than the mean. So if you have a set score of 1, so you basically take your individual X, you know the mean, you know the standard deviation, and you get a set of +1. Then you know the child is like, it's doing well, but shouldn't go more than like 2 above the mean, right? So then you have to look in the other direction. If it has a set of -1 or a percentile that corresponds with a set of -1, because no clinician is gonna love set scores. Well, it's not true actually. So essentially you know, okay, so there's actually on the lower end of the range of weight. Set scores, for example, you have, for example, I don't know, I guess, I know that, I'm gonna put this. So it is osteoporosis. Do you know what osteoporosis is? It's basically a loss of mineralization, decalcification of the bone, which comes with terrible side effects sometimes. And you do osteodensitometry, which is basically a measure how well calcified is that bone. And you're using the individual, the patient, as his or her own control. And you basically measure the change over time as a set score from that reference value. So set scores and T-scores, forget about the T-scores, but the set scores are basically these reference values to an overall population again, and you see the change over time as a development in reference to a population. So you again use set scores for osteodensitometry. So it is, statistics will haunt you. So the concept is important. The individual value is like, you likely will not use minus 1.13. I agree with you there, but it is just one stepping stone to essentially go somewhere where it's practically used. It's also for hypothesis testing. You will be using quite frequently 1.96, which is basically where you have 2.5%, because this is what we will be using for hypothesis testing, because 2.5% on both sides of the distribution adds up to 5%, which is the magical p-value of 5%, above which you will accept your null hypothesis, below which you will reject your null hypothesis, and you will state it as a significant difference between whatever hypothesis you test. Yes, yes. For a set test, which is the simplest form of hypothesis testing, which we will do on Wednesday, it's that set score, yeah, 1.96. The chi-square is a different one. Chi-square, that's a different one. That's actually a right-skewed unimodal distribution that essentially only is being used for a one-sided hypothesis test against the chi-squared exceeding a critical value. We're getting to that in chapter 17. Yep. Yes.
So uses a p-value is
The p-value has a corresponding z-score. Yes.
what is
Well, it's a probability value. So we're getting to that at the end of the lecture. Do you remember that we talked about null hypothesis and alternative hypothesis? Yeah, null hypothesis. You are assuming that you're stating there is no difference between my sample mean and the population mean. And I am certain this is not so. And you basically are testing this null hypothesis. And if you are finding a probability that is less than 5%, you're actually rejecting the null hypothesis because you are 5% certain that this is not coming. And there's only a 5% chance left that it's still coming from the same distribution, but it is at a certain probability from a different distribution, and it's not identical to the population mean.
and this is a half. What is this? Something about like a half score.
A happiness score. Yes, the happiness score. Yes. The happiness score is our example here. Well, which is not necessarily that important. That was just illustrating the sample size. And the increase in sample size leads to an increase on this normal distribution, representation as a normal distribution. It's just, so this is basically data, and you have this data attached on the module. So this data, and this would be something for the lab. This data is essentially the happiness score of different countries.
What is that?
That is, that's a good question. So it's a psychometric test where you ask somebody in the form of a questionnaire, how happy are you?
Oh, it's not like the math.
No, it's a use case. It's a use case for this whole exercise. So it's like it's a survey, and psychological surveys basically have like some outcome metric, which is usually be it happiness, be it quality of life, being walkability, being, I don't know, there are like a million of those. How depressed are you? Back depression, mental. So there are a million of these psychometric evaluations, and the happiness score is just one of them.
And then you use this chart in order to find the z-score.
You calculate the z-score and you find the corresponding p-value. Or you are interested in a certain p-value, you find the p-value, and then you have the corresponding z-score. So it goes in both directions. The number changes. No, the chart, because the chart is a consequence of this mathematical function. Was it? This mathematical function. So this mathematical function defines that curve. So this probability, this P, is essentially, I assume all of you are comfortable with the concept of an integral, which is basically quantifying under a mathematical function the area under the curve. So that area under the curve, the area under this distribution curve is 1. Everything to the left is a certain value. Everything to the left of set minus 1 is less than 84%, 16%. So you basically, you have this as an underlying construct, as an underlying function. You quantify the entire distribution curve as 1, and then you're just defining those areas under the curve under the respective set scores. So this never changes. And that, so we could hypothetically calculate with this function each percentage in the set score table. You can hypothetically do it in Excel. There are actually Excel functions which I spare you from, but so there are Excel functions that can actually do that. Quite simple ones actually. They're not terrible.
So the chart is just explaining that.
Correct. Yes. So this here on the side is basically just relating this association. So you can study it a bit. You basically, you can also with norm inverse, norm dist. With norm dist, you can basically calculate with an x. So that's 73, mean of 70, standard deviation of 10, cumulative true. You can quantify your actual p-value. So this is the formula that I can use to basically express everything on the set score table with an Excel function. The reason why I'm not doing it, because I think there's value to understand the set score table and how these are being read, although these are antiques, relics, right? Like nobody uses this anymore now. This was Excel and R. Nobody uses set score table anymore. But there is merit to understand that there have been tables being used for this purpose. Well, you will need to read p-values and set scores, yeah. So you will definitely have to do it for the courses. But if you rather,
Because that equation.
exactly, that spares you from having to use the equation, yeah. Yeah. Okay. But again, this formula with norm dist allows you to actually quantify exactly that p-value that you're after. All right, any other questions? No? Good, so what did we start? Okay, so p-values, probabilities or proportions can be read from set scores in the set score table. You're reading this, the rows give you the set score up until the first decimal, and the second decimal is being read from the columns. So if you want minus 3.46, you go to minus 3.4, that row, and follow this row until you have the second decimal of 0.06. All right? Good. So, okay, where did we stop now? So apples and oranges. So we compare apples and oranges and emotions. Set distribution, set scores, normal curve, yeah. So now this segue, and to understand why we're actually doing this whole exercise. So yeah, so percentiles are definitely important in the context of various use cases. For hypothesis testing, it's important to understand another concept. So if you draw a sample from a population and you get a mean of that sample, that mean is not necessarily representing the mean of that population. There's actually quite some variability between those estimates. So if you take one sample, you can't be certain that this mean is really representing the population. So you draw another sample, you get a second mean. Now you draw another sample, you have 3 means now. If you draw this 100 times, you get 100 different means. If you draw this an infinite number of times, you basically get an estimate of a variability of these means that you have drawn. And this variability of these means is related to the standard deviation that you have in your population. So the population, the variability in the population will give you an idea how much variability will you have in those means from that samples that you have drawn, those repeated samples. You take a sample, you drop it back, you get one mean. You take a sample, you take a mean, you drop it back in the population. So you get a large number of these means, you get a certain kind of variability. And this distribution of the sample means will be normally distributed even if the population is not, because it's just means, right? So you have a distribution of the sample means. This will always have a normal distribution, would also be smaller, so less variable than the standard deviation, particularly the standard deviation of the population, which is traditionally much larger because you have outliers in your population that you may not have in your sample. So this is reflected in these two statements. So it's normally distributed, even if the population is not normally distributed, and it's less variable than a distribution of individual scores. Therefore, Nolan and Heinzen show this graph. So here is a distribution of the scores, which shapes like a normal-ish kind of distribution. However, if you take now these scores and you create the distribution of the means, so you sample from these 157 happiness scores from 157 countries, you sample repeated samples. You take the sample, you get a mean. You take another sample, you take another mean. You basically get distribution of the means, which is here quite narrowly distributed with one mean that basically reflects most likely what should be representative of the population mean. And that's the idea. So now we have this mean. We assume this mean to be the mean of means, and we want to quantify the variability around that mean. So this is now characterizing the distribution of the sample means. And this is related, as I said, this is related to the standard deviation of the population. And it's related that the standard deviation of the population is divided by the square root of the sample size of your sample, because the larger your sample, the more likely your sample will reflect your population mean, right? If you want, let's say you want to understand the average blood pressure in the population, and you're drawing 10 people, that blood pressure estimate, that mean from those 10 people are unlikely to represent the mean in the population. However, if you sample now 1,000 people, then we're looking now at a more accurate estimate, right? That makes much more sense. As a consequence of that, all these estimates that are reflecting the population mean more accurately will have also less variability. Thereby, this relationship between the variability of these sample means to the standard deviation is here diminished, or is here divided by the square root of the n. So the larger the sample, the smaller this variability of those sample means, because the standard deviation is divided by it. So the larger the denominator, the smaller the variability, which will have ramifications for hypothesis testing. Yes, please. The sample size. The sample size of your sample. So basically a larger n, larger sample size, smaller variability, because you get a more accurate estimate, which will have less fluctuation around. It's good. Yes, so a larger sample size, n, will, by dividing the standard deviation, result in a lower standard error of the mean, which is this sigma. So this is the variability of those means, the variability of these. So you basically have individual scores. Individual scores give you a quite wide variability, but you want to relate this to the variability of your mean estimate. So if I have a sample mean, I want to estimate is like, what's the variability around that sample mean, given that variability of the population and given the size of my sample, I want to understand how much that sample mean likely will vary. And this is being done by assuming that this mean of your sample is the mean of means, whereas the standard deviation, the standard error of the mean derived from the population standard deviation divided by the square root of the n gives you an idea how much variability one would need to expect around that mean estimate from your sample, given your sample size and that standard deviation from the population that we have given. Yeah. I know it's late and it's a little bit hard to digest that. But literally, this is your pathway into hypothesis testing. So please rewatch the lecture recordings. I will post them for both, and there are some further explanation. And we will talk about this again next week, on Monday, next class. This is one of the most important concepts there is in hypothesis testing. So it's like this is super important to understand. Good. Okay, so standard deviation informs the expected variability around that mean that you have from your sample. And this, so you have here distribution of scores, that's your population. That is the distribution of means that you would be expecting based on that variability from your population. And that distribution of the mean is the distribution of the mean that you will be using to quantify your set, which is now becoming your p-value. Because if you're calculating now the mean of my sample minus the mean of the population, which is here, mean sample is m, mean population is mu. If I calculate the difference between my sample mean and my population mean, and then I go on and I standardize this difference by my standard error of the mean, that's how I'm characterizing these differences. And that's when I can say, okay, so my difference between sample mean and population mean is with a probability of tail less than 2.5% or less than 5% with both tails, different from my population mean. Yeah. So you're looking at quantifying a difference between a mean and the population mean. There's a certain difference, right? So if happiness score example 70 versus happiness of the world population of 75. So now I'm quantifying the variability of those means. So I had a sample of 10 countries that gave me 70. So now I know when I have a certain standard deviation, which I know from the population, from the world population, I know the standard deviation is 10. So I'm calculating now 70, which is the m, minus the mu, which is 75 from the world population, divided by that estimate of the variability, which is essentially it's 10 divided by the square root of 10.
What's the estimated?
That's this guy. So we have here the population standard deviation divided by the square root of the n of the sample size, which means that my individual sample estimate of the population mean, of that sample mean, is essentially will result in a certain variability based on that sample size. So that means if you draw another sample, it will not be the same mean, it will be a different mean. And this repeated sampling will create here a distribution of the means. And this distribution of the means will, in a perfect world, it's the exact same as the population mean. So the peak, this mode, this mean of means, will be identical to the population mean. It's not likely. In many cases, it's not. And this is what you want to test. This is your alternative hypothesis with hypothesis testing. Your null hypothesis is exactly the same. Sample mean and population mean is the same. Your alternative hypothesis is that they're different. And so now you're testing the similarity, so to say, and the probability with which this sample mean is identical to the population mean. It's likely not, yeah, because you draw a smaller sample, and the smaller sample gives you like some variability, right? And that variability you mean to quantify, and you're doing that by assuming that if the population has a variability that is to a certain extent, you likely will have different mean estimates, and this different mean estimates will differ according to the variability in the population. And this relationship is the central limit theorem. And that's the segue into hypothesis testing. So, and you then go on and calculate the set score based on these differences. You're standardizing these differences. So the M minus the population M is essentially now being standardized as that assumed hypothesized variability based on the standard deviation from the population divided by the size and the square root of the size of your sample, because smaller samples vary more, larger samples vary less, and they will give you a more accurate estimate. And you're standardizing now that difference, and if that exceeds the outer tail of your distribution, your standardized distribution curve of those differences, then you're rejecting, because then you know it's outside of the bounds of your population, of a net sample population, sorry. Yeah, I know it's a little hard to swallow. I know it's not an easy concept, but we'll talk about it again. Please rewatch the lecture recording. Let's talk about it again on Monday, Wednesday. Okay, so even skewed distributions, if you calculate the distribution of the sample means, will be normally distributed. And yeah, so 1.96 in a two-sided hypothesis test, a set score of 1.96 constitutes the tail below which you have 2.5% of your population, or the P, the probability of your function of these differences. Equally on the second tail, because you do something which is called two tails testing. So you assume both tails need to be taken into account for your threshold. So you basically take 2 times 0.025, which gets you to a set score of minus 1.96. Nolan and Heinz want to make the point. I'm not really sure I agree with that point, but they may have a point, but who knows. They're making the point here that a lot of publications, a lot of published papers gravitate around a set score of 1.96 in their estimates. The reason for this is because they all want to show a significant difference, and thereby they're squeezing and massaging, and they basically get their data somewhere to 1.96. I'm not sure it qualifies as cheaters, but this is what they hypothesize in their book. However, it seems that there is kind of an increased prevalence of papers that are stating a set score around 1.96, which may be something to be considered, that there is some favoritism of researchers to get towards a set score of 1.96 because it associates with a p-value of 5% or below. Good, but that's this. Okay, any questions? That was a good start in a new part of the semester, right? It's a tough start, I know, but it's essentially, it will become clearer. It was your first day back in class? Mm-hmm. Okay. That was a good start. Okay, good. Thanks so much. Have a good evening. See you on Wednesday.